So Dijkstra's algorithm allows us to find the shortest path between any two vertices in a graph. We can represent a computer network as an undirected weighted graph where the nodes are routers, for instance, and the weights are the cost to send a packet from router to router. In our example, we're going to be sending a packet from this source vertex to this destination vertex 5, so from 0 to 5. We're going to be looking here visually at Dijkstra's algorithm. So first, we're going to start with our weighted graph. We're going to choose a starting vertex, which we're choosing as this blue one here. And we're going to assign the paths weights for path lengths for every single other vertex to be infinity. And then we're going to go to each surrounding vertex, neighbor vertex of the starting vertex that we're interested in, and update its path. So here they're both 4. So we're going to update these vertices to have a path length of 4. Then we're going to visit this vertex and look at all of its neighboring vertices and do the same thing. We know that 4 plus 2 is greater than 4, so we're not going to update this vertex weight. Similarly, we're going to continue. We're going to look at all the neighboring vertices of 4. So we have 7, 10, and 5. We'll update those path lengths. So 4 plus 3 is 7. 4 plus 6 is 10. 4 plus 1 is 5. We've updated all these weights. We'll continue. You look at 5 plus 3 is less than 10 from here, so we're going to update this weight to be 8. Then finally, you can look at 7 plus 2 is 9, which is not less than 8, so we're going to leave this as 8. So this leaves us with a final graph that looks like this with all of the path lengths updated. So from 0 here is 4. The shortest length is going to be 0 to 4, 5 to 8 right here. So in our example, I have some code that I've written that will calculate Dijkstra's algorithm. And for my situation, I'm using a directed graph, which uses an adjacency matrix to represent the graph that looks like this. Because it's a directed graph, I'm pretending it's undirected by just adding an edge, 2 edges between each vertex. So here are the vertex names 0, 1, 2, 3, 4, 5. So between 0 and 1, I have a weight of 4, and 1 and 0, I have a weight of 4, etc. Finally, I'm actually going to run Dijkstra's algorithm from a source vertex of 0, and this is going to return an array where each index in our adjacency matrix has the weight from the source to that vertex. So from 0 to 0, the path length is 0. From 0 to 1, it's 4. 0 to 2 is 4, 5, 7, 8, just like in this graph here. And I figured I would just step through the debugger to show you how Dijkstra's algorithm kind of looks as you're running it. So put a breakpoint, debug, and we can go in. So make this a little bigger. We start with our visited vertices here, and we're going to create a priority queue for all of the neighboring vertices of our source, which we're starting out as vertex 0. We're going to put it into the priority queue, and we're going to continue iterating over our graph while we have until we have visited every single vertex. So we're first going to take our first thing out of the priority queue, which is source 0 here. For every single, so it's not yet visited, so we're going to add it to our visited vertices dictionary. For every single neighbor of our vertex, we're going to look at the weight of our neighbor and push it into our priority queue with a weight of the distance plus the weight of the neighbor. So we're getting a total path length here. And so we can continue doing this for every vertex here. And we'll priority queue. So you can see we're currently still on vertex 0, and we push these other two neighbors into the priority queue. So we can just continue stepping through here. We're now on vertex 1. Put all of its neighbors in the priority queue and update all of the path lengths. Now we're processing vertex 2. You get the idea, right? So processing vertex 3, update all of its weights. So yeah, Dijkstra's algorithm is a very classic algorithm. You can find the pseudocode on Wikipedia. But this is the idea. You're just going to continue processing the entire graph and update the lengths here. We can continue stepping through the rest of this quickly. And finally, you can see this is what our visited vertices looks like. So from 0 to 0, we have a path length of 0, 1 is 4, 4, 5, 7, 8, which looks exactly like this graph that we have here.